This is a presentation I gave last week at the IEEE High Performance Extreme Computing Conference. And the topic is on trace replay simulation of MIT SuperCloud for studying optimal sustainability policies. This was work I did in conjunction with my colleague Matthias Mayterth at ORNL, and also Damien Fay, who's with HP Labs in HPE Ireland. The main idea behind this work is to combining digital twins with reinforcement learning, so we can explore new scheduling strategies that balance throughput, energy, and carbon footprint. So the AI race has become a powering AI race. Data centers like xAI's Colossus already draw hundreds of megawatts. OpenAI's Stargate will exceed a gigawatt, and Meta's Hyperion may consume up to 5 gigawatts. This number seems to be continually changing when I search the news. I also recently learned about a data center that Amazon's building in Georgia. It's an $11 billion data center. So the challenge with some of the workloads or the power consumption dynamics of these data centers, or they can generate huge, tremendous swings in power in just milliseconds. So this is a day on Frontier where we're running a lot of HPL type benchmarks, and so you can see these massive swings from 7 megawatts up to 27 megawatts back and forth. This is just a data set I found on the internet of a data center, and they mentioned like 6 megawatts to 30 megawatt spike in 290 milliseconds. So this is a training run, large scale training of AI. And so these are huge challenges for utility companies who are working, who are trying to predict like the power demand, to try to meet the power demand. So there's efforts like EPRI's DC Flex that are trying to address these kinds of issues, and we've been talking with them about how to use our digital twin tools to be able to make power predictions. There's also a lot of concern about carbon footprint at data centers. So there was a recent DOE workshop on reducing data center carbon footprint, where they were interested in all these kinds of issues. So this is where ExaDiGIT comes in. It's a digital twin framework with 3 key components: resource allocator and power simulator, we call RAPS, thermofluidic cooling model, and visual analytics via AR and dashboard. So it has that augmented reality component and a dashboard, and we can replay telemetry, system telemetry, through the digital twin at multiple levels to do these kind of studies, like what if studies, and study how scheduling, power, and cooling interact in one integrated environment. So ExaDiGIT is well established. We modeled about a dozen HPC systems worldwide. We built an open source community of more than 150 members from 42 organizations in 10 countries. And we've also recently won both an R&D 100 award and a UT Battelle award for a Distinguished Innovation Award. So this is just a picture of our desktop version, virtual version of Frontier, and this is my colleagues Cedric and Matthias with Microsoft HoloLens 2 headsets on, and basically they can interact with a virtual version of the Frontier supercomputer, and they can replay telemetry through, and they can actually open up cabinets and look at power and different things like that, and perform what-if experiments. We also have a console interface for running simulations, and we have a dashboard interface that was designed for operators to use to run some experiments. And we're looking at now doing like live forecasting of what the power's situation is going to be like tomorrow from given what jobs are running today. So we've already used ExaDigiT to evaluate scheduling policies. For example, on the Marconi's PM100 dataset, this comes out of Cenica, the Cenica facility in Italy. And this is data from the Marconi, Cenica's Marconi 100 system, IBM Power 9 system. And we've tested incentive mechanisms like Fugaku points. This is a way to sort of incentivize users to use less power. And basically, if you use less power, you're awarded points that you can later use to do like a priority boost in your jobs. So when this paper came out at SC24, all the work had to be done on and tested on the physical Fugaku system, but we can actually evaluate these kinds of policy decisions and incentive structures on a digital twin, not having to use a physical HPC at all. And so we wanted to, you can see all the different data sets, that open data sets that we were testing our different models on, and different virtual digital twin systems we built of each of these. And so we wanted to extend this work by adding the MIT SuperCloud dataset and also training an reinforcement learning agent to optimize these policies. So the MIT SuperCloud dataset covers nearly 400,000 jobs across 260 days. It's 2.5 terabytes in size, with GPU traces at 100 millisecond resolutions. The green AI accelerator system itself is heterogeneous, with both CPU and GPU partitions. So the CPU partition has 480 nodes with 2 CPU Xeon Platinum processors, and the GPU nodes have 224 nodes with 2 Xeon Gold CPUs and also 2 V100 GPUs. And then these actually use multi-tenant scheduling, something called triples mode, and the GPU traces are collected at 100 millisecond intervals. So for all these reasons, this became much more difficult system to model using our digital twin. So we actually had to extend our digital twin quite a bit to be able to handle heterogeneous systems or multi-partition systems, as well as being able to handle multi-tenant scheduling and being able to handle traces that were like less than a second. Generally, we've been working with traces that were somewhere between 10 and 20 seconds. But I also wanted to point out something. The original data set, when it was published on their website, the website here, it mentioned that one of the main purposes was to develop improved scheduling policies, identify inefficiencies in resource utilization, lower energy power consumption, and develop efficient approaches to data center management. So even though this challenge is sort of has long passed, we still thought we'd like try to approach this problem with its completely new technique, and that is digital twins with reinforcement learning. So reinforcement learning is a natural way to approach this. RL agents learn policies that maps states to actions. So we want to learn a policy which is going to tell us, like, depending on what state the system is in, what kind of action should the scheduler take? What's the optimal action? So the way this looks like is we have our digital twin, or what I'm calling now a virtual supercloud, and we have our RL algorithm, and the RL algorithm is making decisions, and then it's returning back the system state and also the rewards objective. And so the training happens by trying out a bunch of different scheduling decisions and seeing how the environment's going to respond. And over time, this should learn to make optimal decisions. And so generally, you have to provide the current state, which in our case is like the job queue, resources, power, and throughput. Actions can be dispatch, backfill, or place certain placement of jobs. And then we can define a reward, which can be a function of jobs completed, power consumed. So we want to basically maximize jobs completed and minimize the power consumed and the queue length. And for this, we used stable baselines 3 to turn our resource allocator and power simulator wraps into a GEM training environment for RL. And this is just some very early results. We just got everything working, and we still have a lot of work to do to prove this system out and prove this method out. But here you can see during the simulation, we're getting at, you can see time updates, and you can see average power of the system, carbon footprint or carbon intensity, system power, efficiency, total energy consumed, jobs completed, jobs still running, throughput, and then you can see some parameters on the RL training. So this is like episode, reward, mean. And the interesting thing, so we did some initial verification tests where we said, okay, let's just fully load the system, run everything 100%, 100% CPU, 100% GPU. And interesting thing is that it gave us that the system was using 1472 kilowatts. We looked up what the top 500 reported power was, and they were using 1436, which is quite close, within 2 to 3%. So that was just a sanity check. Also should mention that we still have a long way to go on getting this actually training, but we were seeing some decent trends where actually the reward function was starting to is increasing here. So far we built so what we had to do to get our system working with ExaDigiT wraps was we had to build a custom data loader for the MIT SuperCloud, and we're able to replay and reschedule jobs, and we show that early PPO training runs. This stands for Proximal Policy Optimization. It's a type of RL algorithm. We're able to show improving episodic rewards, and then we're collecting metrics such as throughput, carbon intensity, and energy consumption. There's still a lot of challenges. So one of the difficulties is that it's hard to do a scheduling problem. For a good scheduling problem, you need to have jobs built up in the queue. However, with these kind of multi-tenant schedulers, it's possible that the queue might be unloaded. That means not a lot of jobs waiting in the queue, so things are getting submitted almost immediately when they are getting dispatched almost immediately when they're submitted. So because of that, we have to find a good time window where that defines a good scheduling problem to really demonstrate out this whole process. And I just want to thank Albert Ruther, who's the lead of the MIT Lincoln Laboratory Supercomputing Center. He helped us quite a bit with the MIT SuperCloud dataset to understand some of the issues. Thank you very much.